Hello everyone and welcome to the Kalman filter tutorial. In this tutorial we will learn how to derive the Kalman filter equations by using an easy to understand and an elegant approach that relies on the recursive least squares method. Before I start, I would like to mention a few things. First of all, those of you who follow this channel or who are my subscribers know by now that I always create a post that nicely summarizes everything that I will explain in this video. And consequently, here is the post. This post contains all the equations, it contains derivations, and it contains graphs. A link to this post is given in the description below this video. Secondly, it took me a significant amount of time, energy, and planning to create this video tutorial and the post. And consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Okay, so let's start. Our plan for today is to derive the Kalman filter equations. Before watching this YouTube tutorial, I strongly advise you to click over here and to briefly go over the derivation of the recursive least squares method. Or you can watch these two YouTube videos that I created and that explain how to derive the recursive least squares method. Secondly, I strongly suggest you to click over here and to briefly read this tutorial on how the state vector expectations and covariance matrices are propagated through time. Even if you don't read these tutorials, you can still follow this YouTube video. This is because in this YouTube video, I will briefly summarize the main ideas of the recursive least squares method, and I will explain you how to propagate the expectation of the state and covariance matrices through time. We are considering the following state space model of a dynamical system. K is the discrete time instant. Xk is the state vector at the discrete time instant k. Uk minus 1 is the control input vector. Wk minus 1 is the disturbance or process noise vector. We assume that Wk is wide, zero mean, uncorrelated with the covariance matrix given by Qk. We assume that this covariance matrix Qk is known. Ak-1 and Bk-1 are state and input matrices. Ck is the output matrix. Yk is the output vector. And Vk is the measurement noise vector. We assume that Vk is wide, zero mean, uncorrelated with the covariance matrix given by Rk. Again, we assume that Rk is known. This is a time-varying system simply because the system matrices A, B, and C are depending on the discrete time index k. And of course, all the derivations and explanations given in this video are directly applicable to the case of time invariant dynamics. That is, when your model is represented by the classical equations of a linear time invariant state space model, and usually in many control textbooks you can see something like this. And the output equation is here again. It's very important to emphasize that the covariance matrices Rk and Qk, as well as the system matrices Ak, Bk, and Ck are known. Then under these assumptions, the goal is to design an observer or an estimator that will estimate the state vector dynamically. Next, we need to introduce three very important concepts, and these concepts are a priori state estimate, a posteriori state estimate, and covariance matrices of estimation errors. In Kalman filtering, we have two important state estimates. These state estimates are the a priori state estimate and the a posteriori state estimate. Apart from this YouTube video and Kalman filtering, a priori and a posteriori are Latin phrases whose meaning can be understood by reading this Wikipedia page. So if these two terms are new for you, my advice is to read this Wikipedia page and you will learn a lot about these two phrases that are used widely in science and philosophy. The a priori state estimate of the state vector x at a discrete time instant k is obtained implicitly on the basis of the output vector measurements y1, y2, up to yk minus 1. That is, the a priori state estimate is obtained on the basis of the past measurements up to the current discrete time instant k and not, this is very important to keep in mind, not on the basis of the measurement yk at the current discrete time instant k. And usually the a priori state estimate is denoted like this. X denotes the state, hat denotes the estimate, k denotes the discrete time instant, and minus the sign over here in the superscript denotes that this estimate is actually the a priori state estimate. Okay, again, keep in mind the following. The minus superscript originates from the fact that this estimate is obtained before we process the measurement yk at the time instant k. Then, the a posteriori estimate of the state x at the discrete time instant k is obtained implicitly on the basis of the measurements y1, y2, yk minus 1, and yk. This is the difference. So the a posteriori estimate is denoted by the equation number 3. So here's the notation. X stands for state, k is a discrete time instant, hat is an estimate, and plus symbol in the superscript denotes the a posteriori state estimate. Here, again, it should be kept in mind that a posteriori state estimate takes into account the measurements at the discrete time instant k. That is, it takes into account yk. In my previous tutorial and in the accompanying YouTube video, I explained how to derive a recursive least square method from scratch. And you can find this tutorial by clicking over here. So if you click over here, you'll see this page. And this page contains a very important part related to the estimation error and covariance matrices. Basically, the estimation errors are defined by the equation 17. We take our true state, we subtract from the true state the estimate, and we obtain our error. Then, the covariance matrix, or better to say the covariance matrix of the estimation error, is equal to the expectation of our estimation error times the estimation error transpose. So this is a general idea for defining the covariance matrices. Now let us go back to our Kalman filter tutorial. Since we have two state estimates, that is, we have the a priori state estimate and the a posteriori state estimate, we need to define two covariance matrices. The first covariance matrix, or better to say, the covariance matrix of the estimation error, is defined by this equation. Here, the letter P denotes the covariance, K denotes the discrete time instant, and minus denotes the fact that this covariance matrix is the a priori. That is, it takes into account the a priori state estimate, as you can see over here. Similarly, we define the a posteriori covariance matrix of the estimation error, and the notation is the following one. P denotes the covariance, K denotes the discrete time instant, and plus symbol stands for the fact that this is the a posteriori covariance matrix. So what do we do over here? We take the estimation error. For example, you can define epsilon k minus as xk minus a priori estimate, xk minus 1. So what do you do over here? You simply take epsilon k minus, this part, you multiply it with epsilon k minus transposed, and you take the expectation. Similarly, you define the a posteriori covariance matrix of the estimation error. Now we are ready to derive the Kalman filter equations from the recursive least squares method. For that purpose, consider this figure over here that nicely summarizes the main idea of the Kalman filter. Let us assume that we are at the discrete time instant k minus 1. And let us assume that we have somehow computed our a posteriori state estimate and our a posteriori covariance matrix of the estimation error. So we computed these two quantities over here. The question is how to compute the a priori state estimate and the a priori covariance matrix of the estimation error at the discrete time instant k. Well, the main idea of the Kalman filter is to propagate these two quantities through the system model or through the system dynamics. And that's it. In that manner, we compute these two quantities. Now, at the discrete time instant k, when the measurement yk comes in, we need to update this estimate, that is this a priori estimate xk hat minus, and the a priori covariance matrix of the estimation error. We need to update them by taking into account the measurement. So how to do that? Well, the idea is to update these quantities and to take information from the measurement by using the recursive least squares approach. So by using the recursive least squares approach, we can compute the a posteriori state estimate and the a posteriori covariance matrix of the estimation error. And that's the main idea of the Kalman filter. We propagate the dynamics, we propagate the a posteriori estimates and the covariance matrix from the previous time step k minus 1. We propagate them through the dynamics, we compute the a priori state estimate and the a priori covariance matrix for the next time step k. Then we take into account the measurement and use the recursive least squares method to compute the a posteriori estimate and the a posteriori covariance matrix for the time instant k. And that's the main idea. Propagate the dynamics, take the measurements, use the recursive least squares method to update and to compute the a posteriori estimates. It is completely understandable if you cannot completely understand this figure at this point. Don't worry about that and don't give up studying the Kalman filtering. You will be able to understand this figure by the end of this video and by the end of this tutorial. Next, let us derive the Kalman filter equations. At the initial time step k is equal to 0, we need to choose an initial guess of the state estimate. And let its chosen initial guess of the state estimate be denoted by x0 hat. And this will be our initial a posteriori state estimate. That is, x0 hat plus is equal to x0. Then the natural question is the following one. How to compute the a priori estimate x1 hat minus for the time instant 1 before the measurements are taken. Now stop for a second and try to think about this problem. So how to go from x0 plus hat to x1 minus hat? The answer is not surprising at all. The main idea is the following one. The states need to satisfy the system model. That is, the states need to satisfy the system dynamics. So we have that xk is equal to ak minus 1 times xk minus 1 plus bk minus 1 times uk minus 1 plus wk minus 1. Since the states need to satisfy the dynamics, the states estimates also need to satisfy this dynamics. However, the issue over here is the following one. We don't know the process disturbance, since we only can estimate the statistics of the process disturbance, that is, its mean and its covariance matrix. And instead of using this equation, we will use the equation given over here, and this is our modified state equation. So we go from x0 hat plus to the a priori state estimate for the time instant 1 by simply propagating x0 hat plus through the system dynamics. That is, through the known and deterministic part of the system dynamics. Besides the initial guess of the estimate, we also need to select an initial guess of the covariance matrix of the estimation error. That is, we need to select P0 plus. If we have perfect knowledge about the initial state, then we select P0 plus as a zero matrix. That is, P0 plus is equal to 0 times an identity matrix. The idea behind this selection is the following one. The covariance matrix of the estimation error is the measure of uncertainty of our estimate. And if we have perfect knowledge, then the measure of uncertainty should be 0. On the other hand, if we don't have any a priori knowledge about the initial state, then P0 plus is equal to C times the identity matrix, where C is a very large number. This means if we don't have any a priori knowledge about our initial estimate, then we say, okay, our covariance is a large matrix. That is, we have huge uncertainty about our initial state. Okay, so now we selected P0 plus, and the question is how to go to P1 minus. That is, how to go from the a posteriori covariance matrix at the time instant k0 to the a priori covariance matrix for the next time instant k is equal to 1. And again, the answer should not be surprising. We use the system model to propagate the covariance matrix. Again, I created a post and a YouTube video that summarizes the main idea of propagating the covariance matrix through time. And you can find this web page and the tutorial by clicking over here. This link will lead you to this page, and this page contains all the explanations. And this equation, that is the equation number 11, is the most important equation for this tutorial. And I rewrote this equation over here and now it is the equation 7 in this tutorial. So, by using this equation, we can propagate our initial guess of the covariance matrix like this. At the time instant k is equal to 1, the measurement y1 arrives. Then the natural question is how to update the a priori estimate x1 hat minus and the covariance matrix p1 minus. To update these quantities, we need to use the recursive least squares method. As I mentioned previously, I derived the equations of the recursive least squares method, and the tutorial can be found by clicking over here. So here's the tutorial. Again, you can read this tutorial. However, the main part of this tutorial is over here. So we have 1, 2, 3 equations describing the recursive least squares method. So here is the idea. At discrete time instant k, we update the gain matrix. So here's our gain matrix. This matrix P is the covariance matrix. C is the output matrix. R is the covariance matrix of the measurement noise. Then once we update the gain matrix, we update the state estimate. And here you can see how the gain matrix comes into the play. Once we update the estimate, we propagate the covariance matrix by using this equation or this equation over here. The equation number 11 is more favorable compared to the equation number 12, simply because this equation is more numerically stable and robust. Now, the question is how to use the recursive least squares equations to derive the Kalman filter equations. First, we need to perform the following substitutions, and the substitutions are defined by the equation 13, 14, 15, and 16. These variables, that is, the first column over here, are the recursive least squares method variable. pk, covariance, and xk estimates. And the second column are the equivalent variables in the Kalman filter. So what do we do over here? We basically take pk minus 1 and we say in our Kalman filter pk minus 1 will be pk minus. Similarly, pk from the recursive least squares method becomes pk plus in the Kalman filter. Then xk minus 1 hat in the recursive least squares method becomes xk minus hat in the Kalman filter, and similarly xk hat in the recursive least squares method becomes xk plus hat in the Kalman filter. Next, let us explain the main motivation for performing these substitutions. Let us first focus on the equation 13. In the case of the recursive least squares method, the covariance before the measurement arrives is pk minus 1. On the other hand, in the case of the Kalman filter, pk minus 1 becomes pk minus, since pk minus is the covariance before the measurement arrived. Next, let us focus on the equation 14. In the case of the recursive least squares method, the covariance after the measurement arrived is pk. In the case of the Kalman filter, pk becomes pk plus, since pk plus is the updated covariance matrix after the measurement arrived. Next, let us focus on the equation 15. In the case of the recursive least squares method, xk minus 1 hat is the estimate before the measurement yk arrived. Consequently, in the case of the Kalman filter, xk minus 1 hat becomes the a priori estimate xk hat minus, since xk hat minus does not take into account the measurement yk. Finally, let us focus on the equation 16. In the case of the recursive least squares method, xk hat is the estimate that takes into account the measurement yk. Consequently, in the case of the Kalman filter, xk hat becomes xk hat plus, since xk hat plus takes into account the measurement yk obtained at the discrete time instant k. After these substitutions, we obtain the Kalman filter equations. We obtain the first equation that explains us and teaches us how to compute the Kalman filter gain kk. So what do we do over here? We take our a priori covariance matrix of the estimation error, we multiply it by the output equation, transpose, and then we multiply it by this part over here. After we compute our Kalman filter gain matrix, we proceed to compute the state estimate. That is, to compute the a posteriori estimate at the time instant k. And the a posteriori estimate is simply equal to the a priori estimate plus Kalman filter gain multiplying this term over here. And this term is the correction term. It's the output minus the output matrix times our a priori state estimate. And after that, we update the covariance matrix. That is, we compute the a posteriori covariance matrix of the estimation error on the basis of the system dynamics, that is, on the basis of ck and kk, that is, Kalman filter gain, and on the basis of this matrix over here, and this matrix over here is our a priori covariance matrix of the estimation error. And you have an alternative form of the covariance matrix, and this is the form. However, it's more preferable from the numerical perspective to use this first form, since the first form is more numerically stable and more robust. By substituting k is equal to 1 in the equations 17, 18, and 19, we obtain these equations that are given by the equation number 20. And these are the recursive least squares equations. So these equations tells us how to update the a priori state estimate and how to incorporate our measurements to compute the a posteriori state estimate. Now, after we compute x1 plus and p1 plus, we proceed further. We take these quantities and we propagate these quantities through the system dynamics. And we explained this previously. So this is the propagation step. We propagate the a posteriori estimate to compute the a priori estimate for the next time instant, which in this case is equal to 2. Similarly, we propagate the a posteriori covariance matrix of the estimation error to compute the a priori covariance matrix for the next time step. So, we'll learn that the two main steps of the Kalman filter are: 1. Before the measurement arrives, use the system dynamics to propagate the a posteriori estimate and covariance matrix of the estimation error from the step k-1 to obtain the a priori estimate and covariance matrix of the estimation error for the time step k. So this is the first step, propagation. Then, at discrete time instant k, we use the recursive least squares equations and the obtained measurement to compute the a posteriori estimate and the a posteriori covariance matrix of the estimation error. So that's the main idea of the Kalman filter. Propagate, measure recursive least squares. Then again, propagate, measure recursive least squares. So these steps are repeated iteratively. Here's the summary of the Kalman filter equations. These two equations govern the time propagation of the a posteriori estimate to compute the a priori estimate for the next time step and the propagation of the a posteriori covariance matrix to compute the a priori covariance matrix for the next time step. And once we propagate the dynamics or propagates the estimates and covariance matrices through the system model or through the dynamics of the system, then the least square or the recursive least squares method kicks in. So here's our recursive least squares method. We take the a priori values, that is the a priori covariance matrix. We use this a priori covariance matrix to compute the Kalman filter gain. Then we use the Kalman filter gain over here and the a priori state estimate and the measurement obtained at the discrete time instant yk to compute the a posteriori state estimate at the discrete time instant k. And then we simply update our a priori covariance matrix. With the system dynamics, we perform several matrix multiplications and we compute the a posteriori covariance matrix of the estimation error. And that's it. So again, time propagation and recursive least squares method. These steps are performed iteratively. Okay, that would be all for today. I hope that you liked this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.